Good morning. So today's lecture is about the compactification of heterotic string on Calabi-Yau manifold. We can also discuss compactification of other string theory, type 2a, b, and type 1. But heterotic string is interesting because we can see directly how possibly a standard model like low energy effective theory can arise from string theory. So before we begin, let me remind you about heterotic string construction. So if you have bosonic string, we are considering the two-dimensional worldsheet mapped to 10-dimensional Lorentzian space. So from the worldsheet perspective, we have 10 scalar fields. Where z and z bar are coordinated on the worldsheet. If we have superstring, then we have map from worldsheet to 10-dimensional space, which is x. And then for each x, we have a tangent space to 10-dimensional space. And so there leaves fermions for left mover and right mover. And so in the case of type 2a, left and right moving fermions have the opposite chirality. When Raman sector has opposite chirality, whereas in type 2b theory, they have the same chirality. And the type 1 theory has open string sector, and I plan to discuss that in the context of D-planes and O-plane later, maybe next week. So heterotic string combines these two features, and so on the left side we consider 10-dimensional superstring. So we have x mu and psi left mu, and well, this can be just left move of x, where mu goes from 0 to 9, and the right mover we have 26-dimensional bosonic string. So that means that we have x mu, where mu goes from 0 to 9. But in addition, there is additional right moving xi. Where I goes from 1 to the remainder, which is 16. Okay? And so x r maps this sigma model worldsheet to 16-dimensional torus. And this has, you can consider consistent string propagation on in this setup because you have separate left moving supersymmetric sigma model, and on the right hand you have non-supersymmetric sigma model at critical dimensions respectively. Okay, so this is heterotic string. Now, there is an alternative description of heterotic string, which is fermionized XR. And that's going to be useful for Calabi-Yau compactification discussion today. So in the alternative construction, we fermionize each Ri. So remember that so when the radius xr is square root 2 times the minimum self-dual radius, then you can actually fermionize psi r to a pair of fermions, or we could say psi right I1, psi right I2, for example. So pair of fermions. So that means that the 16 boson is equivalent to 32 fermions. Okay, and so you can use these fermions to construct symmetries in on the worldsheet theory, which becomes J symmetry in the target space. And if we combine 32 fermions together, it can give rise to SO32 symmetry. So they are rotation group. So this SO32 symmetry in heterotic string arises from the rotation symmetry of 32 fermions. So in this case, we have to treat these 32 fermions together. So for example, what it means is that when we do the spectral flow, when we sum over a spin structure, we have to sum over spin structure together. So namely that we have NS 32 plus NS 32 bar plus Ramon 32 times Ramon 32. What it means is that you can, for example, when you calculate the Paschen function at one loop, you consider NS sector, tensor that to 32 fermions. You can have a sector where you insert fermion number parity, and then we have Ramon sector, and you have Ramon sector bar with parity number. This is Ramon sector. So maybe I should write it in a more useful way. For example, if you have a torus, what I meant is that if you have a torus, we have a two spin structure in this direction and in this direction. So then what you do is that you sum over NS tensor to 32 plus NS Ramon tensor to 32 plus Ramon NS tensor to 32 plus Ramon tensor to 32. So this is how SO32 symmetry can arise. But you can also consider 32 decompose 32 fermions into 16 plus 16 fermions, and consider summing over spin structure separately. By the way, so the reason you want to do that is to make this part of the Paschen function modular invariant. But there are other ways to make this modular invariant. So for example, you can consider doing NS tensor to 16 plus NS Ramon tensor to 16 plus Ramon NS tensor to 16 plus Ramon tensor to 16, and then all together tensor twice. So then you have the same number of fermions, and this is also modular invariant. And this is related to the fact that this in a particular radius of toroidal coparticipation of 16 boson, there are actually points in the moduli space where this happens. Each one of these fermions give rise to actually the E8 symmetry. So obviously, because we are treating 16 fermions together, so this construction has O16, SO16 times SO16 symmetry. You have E8 plus E8 twice because you have two of them. But, so at least this construction has SO16 symmetry, and you have two of them. But it turns out that the Ramon sector also gives rise to generator of symmetry that provide additional generator, and if you combine that, it gives rise to E8 symmetry. So you have E8 cross E8. Okay. Okay. So this is a construction. Now, what it has to do with Calabi-Yau compactification? Well, we will see that one of the interesting thing about. So let me summarize what I just said. So that means that in the case of a heterotic string, in particular, I will be today considering the version of heterotic string which has E8 cross E8 symmetry, because this is one of the most interesting setup which give rise to standard model-like construction. So in this case, the construction has heterotic string, so you have 10-dimensional boson, and then some extra stuff. So let me write it in this way. So what kind of dynamical variable does this heterotic string has? So we have x, which has left moving x and right moving x for 10 dimension. So this is for 10 dimension. And then you have left moving psi, where mu goes from 1 to 9. And then we have right moving side I, where I goes to 1 to 16. And then you have yet another right moving I children, where I goes to 1 to 16. Okay. So this is responsible for E8, and this is also responsible for E8. Okay, so this is what I would like you to remember. So in today's construction of heterotic string, we have these actors: 10-dimensional bosonic variable, corresponding fermionic variable in the left mover. Right mover do not have supersymmetry. However, we have these 32 fermions grouped into 16 plus 16. Okay? So that's the construction we will consider. Okay? And so we'll see how this construction fit into Calabi-Yau compactification later. Okay, so now we're going to start with the low energy description of heterotic string compactification of Calabi-Yau manifold, and later see how that construction can be included in the more full-fledged string theory construction. Okay, so let's first look at the low energy sector. So massless sector. Of the heterotic string. Okay, so in the massless sector of heterotic string, we have gravity, and we have unsymmetric tensor, and then we have dilaton. Okay, so this has to do with supergravity, and there are super partner. So you have metric, and then unsymmetric tensor, and the bosons, and then there are gauge field. Okay. There are also unsymmetric tensor in the Ramon sector, and but today we will set all of them to be equal to 0. Okay. Background string propagating in Ramon background is difficult task. Studying that is difficult task. The Lagrange construction partially addresses the issue, as we'll see later. And then there are fermions. Okay, so and then we are interested in compactification on Calabi-Yau manifold, but preserving some small fraction of supersymmetry. And so first we need to figure out what kind of configuration preserves supersymmetry. We have partially discussed that earlier, and so I'm just going to repeat. So supersymmetry requires that the variation of so this psi is not worthy psi, so maybe I should write. So these are Rarita-Schwinger field, the gravitino field. Supersymmetry requires that this variation to vanish. So if you have supersymmetry variation with variation parameter epsilon, it has this. In general, if you have non-trivial background B mu nu field, then there is a corresponding field strength And then with that field strength appropriately contracted with the gamma matrices can act on epsilon, where H is the 3 form which is related to the field strength. Of B mu nu. I will give you the precise form of this field strength later, but let me write out first the conditions. And there is so this is Gravitino, and then there is Diratino, which is a super pattern of Diraton, which transforms like this. So this is the derivative contracted with gamma matrix acting on Diraton times epsilon and plus a quarter of H. Again, this is H contracted with gamma matrices acting on epsilon. And then you have del chi, and this is gaugino. Which is a super pattern of this gauge field. So you have E8 cross E8 gauge field in this case, so let me write it. So you have E8 cross E8 gauge field. So these are supergravity. Okay, so there is a corresponding gaugino. And then we have minus 1/2, excuse me, of field strength contracted with gamma matrix acting on epsilon, where F mu nu is a field strength of F mu A, which means that F is equal to dA plus A with A, if I use the language of differential form. Okay, so supersymmetry requires that these two vanish. Okay, so these are the conditions. For example, what does this condition mean? So this condition means that F slash, which is F mu nu, gamma nu, and symmetrized, acting on epsilon is equal to 0. This does not mean that the F has to vanish. This means that there must be some epsilon for which this is true. So this only requires that F contracted with gamma matrix has some kernel. Namely, as a matrix, so this is a Dirac matrices. So as a matrix, there is a 0 eigenvalue for this matrix. So this is what this is required. Okay, so this is important because as we will see later, that in the Calabi-Yau compactification, F cannot be trivial. We'll have to take non-trivial gauge field configuration for F in order to have a supersymmetric Calabi-Yau compactification with heterotic string. So this does not necessarily mean that F is equal to 0, but that it means that F has to be chosen so that there is some spinor, epsilon, which get annihilated by F slash. Okay, I haven't told you yet what this field strength is, so let me write that. So actually, field strength is given by the following formula. So H. So I'm going to use the form notation. So let me again clarify my notation. So this is my H, and this is defined to be dB minus 4 over alpha prime. Sometimes in this lecture today, I neglect to write alpha prime. Alpha prime is the inverse square of the string length, square of the string length, trace of omega d omega plus 2/3 of omega cube minus trace of a d a plus 2/3 of a cube. Okay, so this is the definition of the H. Okay, now dB is would be the standard form of the field strength. If this was just that, then it would mean that H mu nu rho is equal to the unsymmetrization of derivative being nu. So this would have been a standard definition of the field strength associated to the unsymmetric two-fold. But as I'm going to explain to you right now, there are corrections. And this correction is important. And this has to do with the Green-Schwarz mechanism. Anomaly cancellation. This was a key ingredient in the 1984 first superstring revolution. Okay, so this looks innocuous, but this was important observation. Omega, so this A is this E8 cross E8 gauge field. Omega is a spin connection, which is associated to the space-time matrix. So in particular, this equation means that the three-form field strength itself is not closed. So namely that Bianchi identity for H is rather interesting. So you know Bianchi identity, which in a classical electromagnetism appears in the first set of Maxwell equations. So you know that Maxwell equation has two types. One is of this type, and the other is this one. Okay, so these are the two sets of Maxwell equation. And this is the first set, this is the second set. The first set is actually algebraic consequence of the fact that F mu nu is equal to del mu A nu minus del mu A mu. So if you write it in this way and substitute it to this way, then it's automatically satisfied. In some sense, the first set of Maxwell equation implies the existence of gauge potential. And then this gives you the equation motion for the gauge potential. That's the structure of Maxwell equation. So this equation of this type is known as Bianchi identity. Okay. In the Einstein gravity, there is also Bianchi identity for the Riemann curvature. Similarly, there is a Bianchi identity for H. If H is equal to dB, obviously dH is equal to 0. So this will be a simple Bianchi identity. However, now H has this correction. So that means that, however, so H is equal to dB minus quarter of alpha prime of trace of omega d omega plus etc. So you have this term. So that means that actually the Bianchi identity implies that this is equal to alpha prime over 4 of trace of R wedge R minus trace of F wedge F. Okay? Where this is a Riemann curvature. And this is the field strength of E8 cross E8. So this symbol trace means different things. This trace means that we are taking trace in the fundamental representation of E8 cross E8. And this means that we are contracting the indices of the Riemann curvature. So these are vector target space index. So this trace means different things, but both of them are fourfolds. And this equation means that we cannot choose, so in order to satisfy this Bianchi identity, we cannot choose the Riemann curvature and E8 cross E8 field strength to be arbitrary. Because Bianchi identity needs to be satisfied. And in order for that to be possible, it is required that the difference of these is a closed form.
Question.
Yes?
Why does Bianchi have to be satisfied? Is this an equation?
This is because H is defined in this way. So namely that H has to be well defined. So the point is that this object in general is not a global form. But the consistency of H requires that this is satisfied. And now I'm going to tell you. So this is non-trivial thing. Why this has to be the case. And I'm going to explain it to you. And this is actually the reason we need that is in order to cancel anomaly. So I haven't explained you why. So let me explain. But first I would like to make this observation that the consistency of Green-Schwarz mechanism requires that the difference of Riemann curvature square and field strength square has to be trivial form. So that means that this and this has to be in the non-trivial cohomology class. Now, in Calabi-Yau manifold, we know that R wedge R makes non-trivial cohomology class. So that means that F wedge M should also be non-trivial. So that means that in order for the Calabi-Yau compactification to satisfy equation motion, we cannot have trivial gauge field configuration. Okay, so that's what one thing we learned. Okay, so let me try to answer your question. So why we need to have this funny thing? So the reason that we ended up having to impose this condition is that the field strength for the unsymmetric tensor field coming from NS sector is not that just dB, but there is this correction. If we didn't have this correction, we didn't have to impose this condition. So, but because of this condition, we need to impose this. Now, why do we have to do that?
My question is, for instance, in Maxwell theory, if you want to add magnetic charges, then dF is going to be the current. So you no longer have the form, but a twisted form. Why can I not have this?
It's a different thing. It's not related.
Okay.
You want to regard this as like a magnetic field strength. Yeah, it's not quite that. There are some similarity, but it's not quite that, I think. Okay, so the origin of this term is to cancel the need to cancel anomaly in heterotic string construction. And in fact, this can be derived top down from heterotic string construction, but this is a way of explaining how things are consistent, why these things can be consistent. So in order to explain that, I need to introduce a notion of anomaly in quantum field theory. Okay, so this is the subject for whole lecture, and I think the elementary particle physics course typically covers this subject. So I'm going to be just brief. So I'm going to use maybe 15 minutes or so explaining the notion of anomaly. Okay, so there are actually several types of anomalies, so it's very important to distinguish. But suppose, for example, there is a quantum field theory has continuous symmetry. And first, let's assume that it's not a gauge symmetry, it's a global symmetry. And the symmetry group is G. So if we typically continuous symmetry in quantum field theory has to be compact. So it can be like a semi-simple Lie group, and like SU2, SO3, etc., or E8. Now, so in such a situation, there is a Noether cell. so that says that there is a current that is conserved, and then generate this symmetry. So namely, that if you define a charge, which is an integral of zeroth component, in general, the star of J, so if we write J as one form dx mu, we can consider Hodge dual of that. So this is one form. So if the space-time is d dimension, this is d minus one form. So then you can integrate that over Cauchy surface. And this gives you the generator of G. And you can exponentiate it to define the unitary operator which implement the symmetry. So this is one step. And if there is such a current, then we can consider coupling it to a background gauge field. Okay? So that means that we deform Lagrangian density by adding coupling like that. And then you can possibly add also field strength or this gauge field, etc. And make that make a dynamical. Now, suppose you don't make dynamical, but suppose you just consider coupling to the gauge field. You are still treating A mu as a classical source. So, in general, if you make this deformation, sometimes this data current is still preserved. But sometimes coupling to the background gauge field can break symmetry. And so when it happens, for example, when divergence of J is not more zero anymore, but is proportional to some non-trivial configuration, non-trivial function of A, then we have we say we have anomaly. So for example, in 2 dimensions, anomaly can take the form of h from mu nu, f mu nu, or d equal to 2. Or in 4 dimensions, it can be proportional to f mu nu, f rho sigma. Okay, having this type of breaking by coupling to gauge field by itself is not a problem. It's not anything that theory has. It does not mean theory has an inconsistency, even though we still call this as anomaly, because as a classical Lagrangian, this should still have G symmetry. So this is an interesting quantum phenomena, but this by itself is not a pathology of quantum field theory. And in fact, this is often useful. So for example, in order to understand the low energy limit of given quantum field theory, solving a complicated dynamical program, this type of anomaly can help us. This can also give rise to some interesting phenomena such as fractional quantum Hall effect, etc. And so these are called 't-Hooft anomaly. 't-Hooft anomaly is caused by non-dynamical background gauge field. Okay? But this can be problematic if you want to make A dynamical, and that in that case we need to find a mechanism to remove this anomaly. Okay, so let's consider the following situation. So how do we diagnose it? So there are various different ways to state the existence of the anomaly. And one useful way to see how the partition function in a given gauge field background behaves. So let me give a general discussion. So suppose the gauge field, suppose that the current has anomaly, and so it's given by some f mu nu, etc. So suppose you have non-trivial function of a gauge field which breaks this conservation of the current. Now, we can formulate this behavior in the language of the Paschen function. So define the Paschen function as z of A. So we are treating A still as a background gauge field. So the Paschen function is a functional of this gauge field. And then we perform path integral. So I'm writing symbolically the integration variable as psi, but the dynamical variable does not has to be fermions. It can have fermions, bosons, and all kinds of degrees of freedom. But suppose you have that, and then suppose you have this Lagrangian, the original quantum field theory Lagrangian, which is expressed in terms of psi, and integral coupling to the gauge potential. Okay, so suppose you define it in this way. So you have this original path integral with quantum field theory Lagrangian, and with coupling to the gauge field. Okay, so now the question is, well, what happens if you shift the gauge field by appropriate gauge variation? So I'm here pretending that it's like abelian, but it can be non-abelian too, in which case it has to be covariant derivative. Okay, so then in this case, this path integral is the same thing. The only place that depends on the gauge field is the second term. So we replace this as a mu plus d mu lambda of j mu. Okay, but now we can integrate by part. So this is equal to d psi e to the minus L QFT plus I of a mu j mu minus I of lambda of d mu j mu. Okay, so but in general this is covariant derivative, so we should also make this covariant derivative. But now we are assuming that there is an anomaly, so that means that after doing this path integral, this should turn into gamma. Right? The gamma can be something like this. Okay, so now I'm still treating A as the background classical configuration. So that means that this is a C number. Right? Because so F is a C number, and this depends, lambda and F are C number, and this does not depend on the path integral variable. So we can just factorize it. So that means that this is equal to gamma of A times exponential of minus I gamma of F mu. Okay, so what this means is that if there is an anomaly of this type, then the path, if you regard the Paschen function as a functional of this gauge field, then the gauge transformation of the Paschen function changes by the anomaly, by phase in general. In general, the anomaly is a real function because J is a Hermitian operator, and so this is just a phase. So the anomaly means that gauge transformations appears as a phase. Okay, so that's anomaly. And if you have anomaly, so the problem with anomaly is that suppose in addition to this you want to quantize gauge field. If you want to, so after this if you want a quantized gauge field, well, then you want to do path integral over A. But the problem is that now you want to use this partial function as a measure for the gauge field, where possibly you may also want to include something like quarter of F mu nu, but this by itself is gauge invariant. But this one is not gauge invariant, so therefore you cannot do the path integral over the gauge invariant configuration of gauge field because integrand depends on, it's not invariant on the gauge transformation. So that's a problem with unknown. Okay. So now comes the Green-Schwarz mechanism. So Michael Green and John Schwarz noticed, well, actually before their work in 1984, a year or so preceding before that, there had been extensive work about anomaly in gauge theory and supergravity theory in diverse dimensions. And in particular, it was noticed that the 10-dimensional type 1 supergravity theory coupled to super-Yamir theory in general has both gravitational and gauge anomalies. And so therefore, such theory in general are inconsistent. And that was problematic in superstring theory because these are some of the most interesting string theory constructions. So Green and Schwarz, however, noticed two things. So when people talk about Green-Schwarz anomaly cancellation, that actually is a combination of two important observations. So one is that in n equal 1 supergravity coupled to super-Yang-Mills in 10 dimension, if G is SO32 or E8 cross E8, and only in these two cases, the gamma of R and F factorizes. So this is one observation. So what this means is that if you, for example, just look at the gauge field part, it takes the form of F mu nu, and then some other things like gamma. Well, gamma is not a good thing, but so gamma tilde of F mu 1, mu 2, mu 3, mu 10 of epsilon mu 1 to mu 10. So namely that it becomes a product of two factors like that. So this is actually an interesting observation because of the following. So namely that what they observed is that for more general group, this type of factorization does not happen, so they themselves have to cancel. But they notice that if the anomaly factorizes, then you can cancel that with a trick like this. So let me explain that. So the idea is the following. So suppose you have original Lagrangian. You add, and this addition is justified in the string theory construction. You add the following term, mu 1, mu 2, gamma tilde, mu 3 to mu 10 of field strength of epsilon mu 1 to mu 10. Well, so this is 2 form, this is 8 form. So basically you are wedging 2 and 8 form and integrate over 10 dimensions. So suppose you have this. And then what you do is that under the gauge transformation, you also assume that asymmetric tensor field transforms in this way. suppose it is the case. Suppose that in addition to gauge, when you do this gauge transformation, then B field transforms in this way. So then in that case, this is exactly cancelled by this coupling, because what happens is that when you have this path integral and you have e to the integral of L, well, if you have addition of minus I of B with gamma tilde, this is gamma. So suppose you have this. Well, now suppose you do this gauge transformation, then this path integral would give rise to something like I times F with F gamma tilde. But this is actually cancelled by shifting B by this. So there is actually lambda. We have lambda trace of lambda F with F tilde, the gamma tilde. So let me write it out carefully. So you have this, but then this term gives rise to minus I of trace of lambda F with gamma tilde, because of, maybe I should have put trace over here, of this one. And they cancel. So this factorization of anomaly allows you to write a counter term to the low energy effective theory to cancel this anomaly.
Question: why does this trace not vanish if
Yeah, because lambda is also taking value in adjoint.
Okay, I see.
Yeah.
I see.
Right? So SO32 has no trace, but lambda is adjoint of SO32. So actually, so this is the product of two SO32 adjoint objects. And so you can have a killing. So this is a killing. This trace gives you a killing. Okay. All right. So this brings us back to this term. So the reason that we have this is that if we just have H is equal to dB, then H is not gauge invariant because of this. H is not gauge invariant because of this. Because B shifted by this, so in general lambda it depends on is on position. So that means that if you have this, the H transforms under gauge transformation. In general, something like trace of d lambda times F. Okay, so therefore H is not gauge invariant. So this ensures that this gets cancelled by this. Because now what happens if I write H is equal to dB minus quarter of alpha prime of trace of omega with d omega plus 2/3 omega cube minus trace of a dA plus 3/2 of a square a cube. One of the features of this Chern-Simons term is that if you change a to a plus d lambda, then trace of a dA plus 2/3 of a squared transforms into a d of trace of lambda with f. So this is exactly what we need because so here I didn't write alpha prime, but if we put alpha prime in appropriate place, then the amount of change of B and the gauge transformation get cancelled by this. So this is related to the Green-Schwarz mechanism. Okay? So Green-Schwarz mechanism require that in order to have a gauge invariant three-form field strength, we have to define it in this way, and that requires that the Riemann curvature squared and field strength squared has to be in the same cohomology class. Okay, so that one should think of this as a part of the equation motion, that requirement for the consistent background for the gauge field. Okay, so we have this H, dH is equal to quarter of alpha prime of trace of R wedge R minus trace of F wedge F. So this is part of the equation motion. So therefore, let me summarize the condition. So therefore, the Calabi-Yau compactification or supersymmetry configuration of heterotic string requires that del psi mu, which is del mu epsilon minus quarter of h slash mu epsilon is equal to 0, and del lambda, the de Latino vanishes, and gaugino vanishes, and dH is equal to quarter of alpha prime of trace of R wedge R minus trace of F wedge. Okay, so these are the conditions. Okay, so in general, this only requires that H R wedge F, R wedge R is in the same cohomology class as F wedge F. But today, I will consider a simpler configuration where H is equal to 0. And we also consider the situation where the trace of R wedge R, so this means the trace of R wedge R is equal to F wedge F. So not only that we require that they to be the same cohomology class, but they are identical. And we're going to impose further condition, which is as following. So omega is a spin connection of space-time, and A is E8 plus E8 gauge field. In order to satisfy this condition, we're going to do some identification of part of the spin connection to the part of the gauge field configuration. So I will explain you exactly how we're going to do that. And that gives rise to the simplest heterotic string compactification Calabi-Yau manifold, where we can in general go away from this most simple case. For example, you can still satisfy this or this condition by changing the relation between omega and h. We can also consider even more general situation where h is not equal to 0. And there have been some extensive study of such configuration. In general, the Calabi-Yau compactification or its variation where h and also the corresponding field strengths for Raman-Raman field to be non-zeros are very interesting and called flux compactification. And in fact, some attempt to construct the Dojita space-time, the space-time with positive dark energy, involves compactification where field strengths of the sum of the higher tensor field, in particular NS2 form and Raman-Raman form, to be non-zero. And so those are interesting discussion, but these are more technically demanding. So for the first introductory discussion of Calabi-Yau compactification, we assume that H is equal to 0, and also we'll make identification of spin connection with gauge field, as I'm going to explain later. Okay, so now we're going to come to the Calabi-Yau compactification. So let me remind you a few things about Calabi-Yau compactification. So I'm going to write it as Calabi-Yau 3 because this is complex three-dimensional space we are going to consider. So this means that we're going to start with 10-dimensional space and then make the part of the space to be Calabi-Yau. So 6 out of 10 dimensions Calabi-Yau, and so we are left with 10-dimensional Minkowski space. Okay, and there are two features that I would like to remind you of. One is that holonomy of Calabi-Yau is SU3. So that means that we can assume that spin connection SU3 part of the spin connection is non-trivial. Okay, so I'm going to open the parenthesis. So in 6 dimension, the holonomy in general is SO6. Right, it's a 6-dimensional space, so spin connection takes value in the spinor representation of SO6, which is the same as a Lie group as SU4. Okay, and this SO3 is basically subgroup of SU3. So therefore, spin connection in general takes value in the agent representation of SU4, but only in SU3 part of SO3. SU3 is made non-trivial. Okay? So this is the Calabi-Yau compactification. And another thing that we're going to use later is that Hodge diamond. Excuse me. This is was a 3-Hodge diamond, then this is 1, 0, 0, 0, H11, 0, 1, H21, H12, 1, H22, 0, 0, 0, 0, 1. And these two are the same. So the Hodge diamond of Calabi-Yau is characterized by 2 numbers. So those are 2 important things. Okay, so we're going to put heterotic string on Calabi-Yau manifold, and by declaring that, we have already set the metric of this 10-dimensional space and the spin connection on it. So now I would like to specify the gauge connection. But gauge connection is specified by requiring that this cohomology, this 4 form is cohomologically non-trivial, so that we can write it as globally defined H. It's important to remind you that H is defined to be globally defined, this was this mechanism, that it's not gauge, H does not change under gauge transformation. So it's a globally defined 3 form. So therefore, this has to be closed. So that means that these are cohomologically trivial. But we're going to go on further and try to actually identify trace R wedge R is equal to trace F wedge. And the easiest way of doing it is the following. So remember that gauge field takes value E8 plus E8. Now E8, either one of the E8 certainly contains SU3. So what we can do, therefore, is to identify this gauge field to be in this SU3 part of this E8. And only that part is non-zero, and that is identified with omega mu, which is also, so this is in E8, which is in E8 plus E8. And this is in SU3, which is in SU4, which is the same as SO6. Okay, so these come from different things. This is, yes?
Question, does it matter which E8 would be?
It doesn't matter. I haven't told you which E8. In fact, I think there is actually a global identification of E8 in the case of identification. But it doesn't matter. It's just a matter of convention. Okay, so we do this identification. So since omega is non-zero, A is non-zero in that sector, so that breaks part of E8. So the commutant of E8, commutant of SO3 in E8 is E6. So this breaks E8, the gauge group to be E8 times E6. So this is a remaining unbroken gauge configuration. This is like Higgs mechanism, where background gauge field breaks E8 into E6. So now this is your gauge field configuration. So this is the simplest compactification. And this also has a very nice description in terms of the worksheet, which I would like to explain now. So I'd like to remind you that heterotic string we are considering consists of these dynamical variables. So I'd like to remind what they are. So X is mapped from worksheet to 10-dimensional spacetime, and we have already combined left-moving boson and right-moving boson. So this is a genuine free boson mapped from worksheet to target space. We have left-moving fermions, and there are 10 of them. There are 32 right-moving fermions, and we are grouping them into 16 for E8 and 16 for E8. Okay. So now we're going to do Calabi-Yau compactification. So that means that X mu becomes now. So now it's originally X mu goes from 0 to 9. But now what we're going to do is restrict the first one to be 1 to 6, and then remainder go from 4 to 10, and these are coordinates of the Calabi-Yau manifold. Right? So that's one thing. And psi mu, psi left mu also decomposes into 0 to 3, and then psi left I, which goes from 4 to 10. And that's for on Calabi-Yau 3-4. And then this one coupled to omega I, the spin connection of the Calabi-Yau space. Okay? So the spin connection coupled to this one. Now, we have these things, so let's pay attention to this part. So I'm not going to touch this one, just look at it. Psi right I, this couple, so I goes from 1 to 16, and this couple to gauge field in E8. But I told you that in the E8, so I'm going to identify this E8 to the one for which SU3 is embedded. So you have SU3 as a subgroup, and this SU3 couples to this gauge. This omega is also SU3. So what we can do, therefore, is there are 16 of them. Then what I'm going to do is to take out psi, this is right, I'm sorry, psi right, of I to 4 to 10 to couple to SU3 part of, so this is, I should have done this like 1 to 6, this was artificial, so this was, take 1 to 6. So this coupled SU3 part of AI. And a reminder, not coupled. To this background gauge field. Okay? So therefore, this corresponds to unbroken part of the gauge field. So this is responsible. So sum of a spin connection of this give rise to E6 symmetry. And this give rise to E8 symmetry. So there are six fermions which couple to A, and there are 6 fermions which couple to omega. I'm identifying omega and A, so it's essentially coupled to the same thing. So now if you combine this, then this gives rise to actually n equal 2 sigma model. That we discussed in the past couple of lectures. So remember that in the last couple of lectures, we considered n equal to 2 sigma model, where we have x mu, xi, and psi left I, and psi right I, coupled to the Calabi-Yau metric. And appropriate spin connections. And this gives you that. And the rest of the fermions and the rest of the bosons couple to trivial background. So therefore, we have been able to successfully decompose this heterotic string dynamical variable to n equal 2 sigma model on Calabi-Yau and the rest of free field. So we know we have a lot of mathematical technique of dealing with this, which can directly translate into analyze this heterotic string compactification. So this is actually the most sort of convenient, simple configuration of the Calabi-Yau compactification where we have lots of techniques to analyze. These are called 2-2 compactification of Calabi-Yau. 2-2 compactification of heterotic string on Calabi-Yau. So this construction is called 2-2 compactification. In general, as I said, the equation motion for unsymmetric tensor field, the Bianchi identity, does not require that A is equal to omega, as I did, only requires that R wedge R trace is the same as F minus F trace in the cohomology class. So that means that we can deviate from this condition. So what's going to happen is that we still have worldsheet supersymmetry for the left moving sector, but not on the right moving sector. So in general, such compactification is called 2-0 compactification. Because not identifying gauge field to the spin connection, not identifying A to omega, breaks half of the supersymmetry. So these are called 2-0 compactification or 0-2 compactification. So in the Calabi-Yau literature, I suspect you often see the terminology of 2-2 compactification and 2-0 compactification. So 2-2 compactification is the simplest setup. 2-0 or 0-2 compactification depending on your left and right convention. A more difficult one, and there are still lots of techniques, but in general, even non-existence of, so for example, in 2-2 compactification, there are powerful tools starting from Yau's proof of Calabi conjecture, and then analysis of renormalization group equation for sigma model, which guarantees that indeed there is a non-trivial conformal field theory for each given Calabi-Yau compactification. Even proving something like that is highly non-trivial. Yes, you have a question.
Question for the 2-2 case, what are the superpartners of psi r? The one that couples two.
So which psi r? So namely that, some superpartner of psi r which coupled A is X here for Calabi-Yau. So I wrote this as 1 to 6. You have 4 to 10, but that's actually I should have said 4 to 1. So maybe I should have write it as 1 to 6. So this Calabi-Yau part of X, this Calabi-Yau part of psi left, and this heterotic string fermions coupled to SU3 part of E6, E8, excuse me, makes superpartner. So it's kind of an interesting sort of mixture of different degrees of freedom. Okay, so that's Calabi-Yau compactification.
Another question. And this identification between A and omega, if I want to understand this as a Higgs mechanism, is there a way to think of some scalar acquiring a value?
Yeah, so we'll come to how you get Higgs field in standard model. So that's also comes from gauge field, but in a different ways. So here, yes, I will come to that point later. So there are scalar field which breaks. So in the heterotic string phenomenology, this E8 is to be identified with E8 of the ground unification. So it is possible to embed SU3 cross SU2 cross U1 gauge group of standard model of particle physics as a subgroup of E6. And in fact, the particle content of standard model fits nicely so that it gives you single multiplet of E6. So it's actually a nice example of superstring ground unification, supersymmetric ground unification.
Is this a 27?
Sorry?
Is this a 27 representation?
Yes, I'll explain it. Yeah, it's a 20. Yeah, indeed. So matter content is in 27. And yes. So yeah, very good. So therefore, in order to reproduce give rise to standard model, you need a Higgs mechanism to break E6 into SU3 cross SU2 cross U1, and that can be done by analog of Higgs mechanism in the context of Calabi-Yau compactification that I will explain later. Okay. So I have 3 more minutes, so let me briefly mention. So I'll discuss breaking a little bit further. So the idea is the following. So if you have a heterotic string compactified on Calabi-Yau manifold, then E8 cross E8 symmetry to be broken to E8 cross E6 because we used decomposition of E8 to SU3 cross E6, and this part is broken by identification of omega is equal to A. Okay. So this E8, we're going to use it as a ground unification. And so the argument representation of E8 E6 is 78, and chiral fermion are 27 and 27 both. And we'll see how they appear in this compactification. Okay, so this is actually, we'll see that this gives rise to a feature that is very sort of favorable for the supersymmetric band unification. Now, originally, E8 only has, in the massless sector, only has non-trivial representation. And so, except for trivial representations, there is an adjoint representation of 248, so one of the perfect number. And this was important for the anomaly cancellation mechanism. The Green and Schwartz are looking for gauge symmetry for which the adjoint representation is dimension 248. And so what is this doing? Well, the one thing is that this E8 is a tensor cross. And originally we are considering adjoint representation of the whole thing. So that means that if you have a non-trivial representation of E8, that degrees of freedom has trivial representation for the other E8, and vice versa. So that means that this adjoint field is singlet for the other E8. So namely that if this were to give rise to the SU3 cross SU2 cross U1 gauge symmetry inside of E6, then these ones are neutral. So this one, in general, in principle, can be used for hidden sector. So one of the promising scenario for dark matter in the universe. So we know that there has to be dark matter in the universe for a variety of reasons. It was originally discovered how the way that the galaxy moves in clusters. That was by Zwicky. But then in the 1960s, 70s, variety of astronomers, including Vera Rubin and Osterreicher, who just passed away, noticed that there is something funny about the way that galaxy behaves. And then it can be explained by postulating matter that do not strongly interact with standard model particles. In fact, the way that this would-be dark matter behaves suggests that they shouldn't interact with each other strongly because there is diffusive property. That the way that so the galaxy is like very plain. So and that is only possible there because there is a diffusive force. And on the other hand, the dark matter makes halo around galaxies. So so they behave very different. There are also, in the past couple of decades, very precise measurement of the evolution of the universe, and there are lots of cosmological data, such as from CMB. And the consistency of the picture also requires dark matter in the universe, in a way that is consistent with observation of galaxies. So, similarly, there are strong evidence that there are large amount of matter in the universe, consisting of objects that do not interact strongly with the standard model particle. And these are like very desirable candidates for such particles. So it's interesting that a heterotic string construction automatically incorporates this. Okay? So I only probably need half an hour or so to complete this discussion. But so therefore, in the beginning of next lecture, I will discuss how actually these chiral fermions fit into this matter sector in E6 grand unification, and provide formula of how many generations we would obtain from this heterotic string construction. Okay, so that's it for today.